Goedemiddag allemaal. Hi, I'm Vincent Salucci. I'm the program maker at the TU Delft Library. I do exhibitions in the cultural programming here. I'm very excited that you're joining us today for the Flying Solo Committing to Wind Energy exhibition and program. This program has been in planning for quite a few years if you count the research stages. We've had begun with some conversations with the Airborne wind energy researchers and learning about the kites for generating wind energy, and then, as all good things, there's just so many connections and so much research on campus that it's actually impossible to cover it all and to tell every story. And for that, that's one of the hardest parts about being a curator. But we try to do our best, and then also it's also about finding the appropriate connections too. And so what we did was we thought about an artist inspiration, and naturally the work of Theo Jansen came to mind on the subject of wind energy. And so we were lucky enough that the library and the academic heritage has already had a connection with Theo. And so we pursued, we had several more conversations, and we were lucky enough to feature him as the feature artist for this program and exhibition, and bring his work. And he's also a former student of the university, and he'll tell you a little bit more about that. And so we made a fun film this summer in which Theo went around campus, some of his favorite spots, and told us some memories. So we'll talk a little bit more about that in a moment. Let's see. And then, of course, there's a vast history once you start exploring the history of wind energy research at the university. And dates back to the 70s, and Gerard will tell us quite a bit more about that. Emeritus Professor van Bussel. And then, so we went into the history of wind energy and the turbine testing, some of the wind tunnel features on experimentations facilities on campus, and then of course the story couldn't quite be told without looking back even a little bit further, and this cultural icon of the Netherlands and the molen and the polar molen, and the significance of the country for reclaiming the land. And one of the most interesting things to me was that there's such a strong cultural identity in this iconic symbol of the wind molen, or the molens, and yet there is let's say some reluctance to fully commit to the turbines. We know about the horizon pollution, and we not in my backyard, and so we that's an interesting juxtaposition to me, an interesting contradiction. I wanted to kind of expose that and have lots of discussions about that throughout the entirety of this program. It's a wide program. We have quite a few events, and so this is the sort of the kickoff event on campus, and it's the opening reception. So thanks again for joining us. And I'm gonna not talk too much longer, but I do need to put out a few thanks first. So let me do that. This exhibition would not have been possible without many, many people and organizations. And so I'm already afraid that I'll omit one or two, but the partnerships and sponsors that we afforded us to be able to do the tram portion of the exhibition, where we're working together with HTM, with Vattenfall, Kite Power, who I see is around here. Yep. I had it first. And the Molen de Roos and Blade Made. So thank you all for your support of this program and your generous contributions, as well as all the researchers and faculty within aerospace, mechanical engineering, IDE, some of the student assistants that are helping out on this project, and we're custom coding applications and doing CAD drawings and things for me, particularly William Costa and Raymer Ritterig. Also, I wanted to thank my colleagues in the library. There's so many of you that are involved in this, from our New Media Center team who's so professionally handling the AV today, to heritage colleagues, particularly the Tresor and Mericha and Cormick, just having access to the study collection in aerospace that we brought in so many of the objects that they were doing some storytelling with, as well as Monique Jansen deserves quite a bit of credit here because she's the graphic designer that I collaborate with as much as I can, and then I think. I'll leave it at that with one more special addition to Marcel Janssen and Sid Kaji in the side over here, hanging out in the wings. This is my production crew that I just absolutely would not be possible to produce a tentoonstelling of this caliber without them. So I'm pretty humbled and grateful for their collaboration. With that, I think I will quit speaking with you, but we're going to have a packed program. Theo's going to get us started, and then we'll turn it over to the wind energy researchers. I'm going to read a brief bios for everyone. So Theo Jansen studied physics at the TU Delft University from 1968 to 75. He spent his early career painting, even making a painting machine here in Delft before deciding to shock the citizenry by making a real flying saucer, which flew over Delft in 1980. Since then, he has been working on the creation of the strandbeest species and evolution of beach creatures animated by the wind. You can see the past species of strandbeest in his mortuarium museum, newly opened in Delft on the Skiwig and the Kabel District factory, former Kabel District. Janssen's work has been shown internationally in museums, books, and several television programs such as The Simpsons, as well as publications like The New Yorker, New Scientist, and Wired. Sometimes written in the old TU Delft library downtown, Jansen wrote a column, Reflection, in De Volkskrant from 1986 to 2008. A selection of these were published in the book Klimmen in de Lucht, Climbing in the Air, and also in the video that we made this summer, Theo told some stories about how the strandbeest actually started in this column as a little bit of an act of fiction, an imagination and writing, and they were particularly inspired by a book, and so I also think that's appropriate to acknowledge in the library. And then we have Professor Gerard van Bussel is professor of offshore renewables at NUS, the National University of Singapore. He is the former chairholder of wind energy in the Faculty of Aerospace Engineering. His research interests cover large-scale offshore wind R&D and rotor aerodynamics, in addition to operational aspects, conceptual design of advanced wind energy systems, and wind energy in the built environment. He is a consultant for the wind turbine industry and advising the Hollandische Molen and several other windmill foundations on windmill biotope issues, and he is a certified volunteer windmiller. And Gerard will also be joining us for the Molen tour at Doros a little bit later on in the program, so I hope you can join us for that too. And then Roland Schmehl leads the pioneering Airborne Wind Energy Research Group as an associate professor at TU Delft. He is co-founder of the university spin-off company Kite Power that develops a 100 kilowatt kite power system. Focusing on the multidisciplinary challenges of AWE, he has also contributed in many ways to the development of the emerging technology sector by organizing the 6th International Airborne Wind Energy Conference in Delft, co-organized follow-up conferences in Freiburg and Glasgow, and editing 2 Springer books about airborne wind energy published in 2013 and 2018. He chairs the technical committee Airborne Wind Energy of the European Academy of Wind Energy and is the founding director of Airborne Wind Europe, the Association of European Airborne Wind Energy Industry. And last but certainly not least, Jelle Poland is a PhD researcher developing and validating next-generation kite design models for soft-wing airborne wind energy systems. His work combines close collaboration with industrial partners, the development of novel simulation techniques, and validation through experimental campaigns to advance kite-based renewable energy. Okay. Got through that. But thank you. And we're going to begin by two brief clips that are rolled into one of the video that we made this summer with Theo on campus. And after that, he'll come up and talk to us a little bit.
Well, I often am requested to give lectures to some wind turbine kind of thing and new energy things, because the strandbeest, they live on the wind, and but I don't think I have something to contribute to the technical knowledge of these people. It's more like a sort of mental inspiration, because what I think the strandbeest do sometimes is that that's what they do with me. They make me see the miracle of life somehow, because I'm trying to do the evolution anew, and then I see more that in fact that we are living in one big miracle. I mean, one of the big miracles, I'm thinking about it every day, is that you landed in your body and I landed in mine, and how my life got about. And I'm thinking a lot about this, and somehow the strandbeest, I notice with people that they give some view on life on itself, yeah, and it's like that as if because our lives are full of agendas and appointments and whatever, but really the essence of life, what we have to do, what life is about, is something we don't think of too much, but we have to, I think, to motivate us to think about the future generations. And it's so I think my work doesn't contribute very much technical solutions for wind energy, for instance, but it might motivate the people, to give them a reason to do something about it. We're standing here at Haagse Hogeschool, and there's a strandbeest here called the Emeritus ventosa, and it's shown here as a natural historical object, as a part of the evolutionary story of the strandbeests. Now, before this building was built, this was a part of the technical university. We as students, we had to learn how to treat metal. So I made a microscope here. And as an unsuccessful student, I'm so happy that I'm back somehow. So I'm so happy that the beast is hanging here. Thank you, Vincent, for your introduction. You're going to do something there?
I was going to get your...
Oh, okay, you're an assistant. Thank you. Great. I have an assistant. Here he comes. Oh, you want me to explain the leg system? Oh, thank you.
Yes.
I will do that. I did it before, you know. It's, well, if you look at the strandbeest, which a project which I started in 1990, I tried to make new forms of life. And I hope that these new forms of life survive on beaches, so they survive the storms and the sand and the water. And one of the characteristics of the strand beasts is the way they walk. And they walk in a way that they stay on the same level while walking. And I will try to explain this. In every strand beast there's a sort of backbone which makes a circular movement like this. And this circular movement is transformed into a walking movement written by the pencil down there. And you see, as soon as the pencil is on the ground, it draws more or less a straight line. And that means that the animal stays on the same level. So that's because of the shape of that curve down there. Now, the shape of that curve is very much depending on the length of the tubes between the backbone and the pencil. If you have another proportion of length, you get a totally different curve down there. And when I started this, I didn't know which ratio of length I needed to get this curve. That's why I wrote a genetic algorithm in an Atari computer in 1990. And after a few months, day and night, evolving in the computer, there came out 13 numbers, which were the length of the tubes which I needed to get this system running. And this you could see as the genetic code of the strand beast. This genetic code I published on my website a long time ago, and since then, hundreds, thousands maybe, of students are using this code to produce their own strand beast, either in bamboo or in aluminum. So there are a lot of strand beasts in the world, and they don't survive very well on beaches, but better on bookshelves in student rooms. And all these students, they have the feeling that they have a nice hobby, that they have a good time. But the reality behind this is that they are used for the reproductions of the strand beasts. So the strand beasts, they reproduce, and they use students to do that. Because as soon as you're infected with the genetic code, you cannot do anything else but making strand beasts. Oh, yeah, thank you, my charming assistant. Can you bring me...
The table? The whole table?
Oh, the whole table, yeah. Great. Are you okay? Wow. Such an assistant. I never had it. I would like to show you an example of one of these students. So this is made by a guy in Amsterdam called Ad Lagerfeld. Let's see. So this is an offspring of the genetic code. You see, it works quite nice, right? And this guy, he used his own code to make a strand beast. It might be better than my code. So it will have more children in the evolution on the internet than my children. And I don't mean my real children, but my mental children are the strand beasts, you could say. And so there is a real evolution going on in cyberspace of animals, and this will have, it's a mutation, you could say, and this mutation probably will have more descendants. Now, I would like to tell you something about the nervous system of the beasts. Would you hold this so that everybody can see it? Just you can stay down, yes. Hey. Well done, thank you very much. So there's a small O-ring on the end, which fits exactly into a tube, so you have a sort of pump. Now, in the movie, you might have seen the wings going up in the wind, up and down, and there are pumps connected to the wings, so they pump air, wind energy, into PET bottles, into spa bottles, to high pressure. And that's energy which the animals need in case that the wind falls away on the beach. They still have some energy in their wind stomach to produce energy and to have, because if you connect a bottle with pressure with this little tube here, this jumps out and you have a sort of muscle. And muscles turn out to be very handy if you want to survive on beaches. A muscle is nothing but an object which becomes longer or shorter on command. And the command is given by a valve which opens here. So the valve you could see as a sort of nerve cell. And if the valve opens, this jumps out. Now, I have a nerve cell here. Here. This is a nerve cell. So as you can see, my basic material is electricity tube, which you probably all know. We use it for cables in houses in Holland. It's a very Dutch sort of project. Only in Belgium they have the yellow kind of tubes. Now this yellow tubes is my protein, you could say. It's my oermateriaal. So this is a valve. If I blow air in here, the air goes in here and comes out of here. But if I push in this piston here, it's blocked. So nothing but a valve, open, close, a nerve cell. This nerve cell is operated by a small muscle. So if I blow air in here, the valve closes and no air comes out of here. If you see this as the output and this is the input, then the output is opposite from the input. Everybody is nodding. What's happening? Oh, okay. But I want to be sure that everybody understands what I'm talking about. That's why I would like to say, if you see this as a person, and this is the mouth, and this is the ear, then the mouth says the opposite from what it hears. If it hears there's air, the valve closes and the mouth says, no, there's no air. And that's why I call this a liar. It says the opposite from what it hears. So we're going to do a small experiment now. Imagine that you are a liar, and that you are a liar, and I'm a liar. I say to you, yes. What would you say to him?
No.
Very good liar, yes. And now you hear no. What would you say to me?
Yes.
And I hear yes, and I say no. So in this conversation of three liars, I changed my opinion. And that's what you have with an uneven number of liars. Then you have a so-called dynamic system. Now, I have three liars here. Let me see where they are. Here they are. So this is you, and this is you, and this is me. Let's see what they have to say to each other. So they're saying yes and no, just like we did. And as you all know, a yes can mean a 1, and a no can mean a 0. So with these liars, you can switch zeros and ones, just like in a computer. Now, in the old days, I studied physics over there, and I remember that I learned something about logic networks with so-called gates. Now, this is a NOT gate for the ones who have studied physics as well. This is a NOT gate, and with a NOT gate you can build any kind of gate. And you can, in fact, what you see here is the beginning of the brain of the strandbeests. And brains turn out to be very handy if you want to survive anywhere, because a brain does nothing but collecting information from outside, the wind speed, if there's water, the hardness of the sand. So with senses, it feels the outer information, does something with that information via this kind of layers, and then give instructions to the muscles to react to the environment. And that's a process which is not very operational yet, but it will come in the future strandbeest. So I think, in fact, that the strandbeest will survive better and better all the circumstances on the beach. And I hope that at the end of my life, that these beasts can live on their own. It's not that far yet, because I have to nurse them all the time, but there is some progression, I could say. So every spring I bring these new animals to the beach. The whole summer I do experiments, and in the summer, in the fall, I'm a little bit wiser how they should survive. And we're slowly going to that project. So Vincent, am I still in my time? A couple of minutes. Okay, so we can do a small experiment. Yes? Okay, well, let's see. I would like to show you the water feeler. This is the water feeler. So this tube is vital for surviving on the beach. It goes over the ground about this height, and it sucks in air all the time. And as soon as it arrives into the sea, it swallows the water and feels the resistance of the water. And then it gives a signal to the brain, and the brain gives the signal to the muscles. So we're going to test the water feeler now. So I need an assistant here. Is a volunteer coming on? Yes, you, yes. Her friend just pushed her on the back. Sorry, what's your name?
I'm Eliana.
Eliana, can you hold this here? Wonderful. So I'm going to pour in a glass of water, and that will represent the sea. I needed some water myself as well. So we're going to put the little tube in here, and then there has to happen here something. Now, we need an indicator that the signal really came into the water feeler. That's why I'm going to connect it with the layers. So I told you that this was more or less a representation for the brain. So the brain is connected to it. So as soon as I put in this tube in the water, you should hear the layers running. Now, I'm not sure if it's really going to happen, but we'll try, Eliana.
We're going to find out.
We're going to find out. Now, I'm going to connect it with some bottles, but before that, I would like to do some safety measures. Are you okay with that?
Perfect.
You probably can't see that well anymore because it's not very clean, I'm afraid. So I'm going to connect it with the bottles. Now it's going to move in your hands. Let me just loosen some nerve cells here. So, and then, yeah, it's going to move in your hands. Are you okay with that? Everybody ready? Let's see. Oh, it felt maybe there was some water in there already. Let's see. Yeah, there is water in there.
Yeah, it's on my shoes.
Yeah, I'm sorry for your shoes.
That will be okay.
Let me see it. I'm going to do something about this. I told you, it might not work, but you believe me, don't you? Sometimes it works. Well, thank you. So you've done so well to take all this risk. Okay, thank you very much for it. The word is to Gerard van Bussel is going to take over from here. I've been talking with him, and I think it's gonna be a great talk. Thank you.
Okay, can you hear me? Yes, perfect. Well, Theo, of course, I do have a miniature strandbeest on one of my bookshelves. And until your presentation, I thought it was rather innocent. Because I'm playing with it, my grandchildren are also playing with that. But now I suddenly realize I need to be careful, because that strandbeest is going to use my ingenuity and then that of my grandchildren to produce more and more strandbeests. I didn't realize so far, so I'll be very careful with giving the strandbeest in their hands, because you don't know what's going to happen in the future. But thank you anyway for a very interesting presentation. I have, by the way, a miniature strandbeest that is driven by a small wind turbine rotor. You know this, one of these small models. Please buy a model of that one. It's fun building it and running it. My presentation is about what happened in TU Delft in terms of wind energy. And you see me here in front of an old windmill. That's because I got inspired into going into modern wind energy by becoming a certified windmiller. Nowadays, students, they need money all the time, so in their free time, they go into the jobs. What I did in my free time is I took the education on becoming a certified windmiller. So during my student times, I was already eligible to run all windmills. And actually, that fired my interest into modern wind energy, because I thought, well, what you can do with old windmills, you might be able to do better with the knowledge that we had those days. This is the right one. Doesn't work. I have to pinpoint it to something. Ah, okay.
Back on.
Okay, right. Since the presentation has a kind of title, Wind Energy in the Past, in the Present and the Future, in TU Delft, and maybe a little bit wider, I look back into the annals of the TU Delft, or the TH Delft, Technische Hogeschool Delft, as it was called in my days when I started. And the first thing I found, in terms of research that was done in Delft, was on the Prinsenmolen. That's an old windmill in Hillegersberg, that's near Rotterdam, in the Prinsenmolen Park. And this was in between the two world wars, 1938 until 42. And it was inspired by the Vereniging de Hollandse Molen. The Hollandse Molen wanted to find ways in order to keep old windmills running. And one of the ways in doing that was in improving the sail system, the rotor system. And on the right-hand side, you can see how a traditional rotor looks like. Also, Molen de Roos has that system. And on the left-hand side, you can see an improvement that was developed together with some researchers from TU Delft. Interesting, certainly when you see into what we did later, is they went to look into the airfoils, and the old windmill sails did not really have airfoils, and these were optimized airfoils that were developed into what in those days was the wind tunnel of the Department of Air and Hydrodynamics in 38. Apart from looking into the sails, they also looked into the flow around the body of the windmill, because there's quite some influence between the body and the sails, as you can imagine. And some kind of patents coming out. Those were not by the professors, but it was by the young engineers, so to say, that did the research. That's how it always goes. And it's good that they get the patent as well. And a lot of the knowledge is still being kept because they published a very important book in old windmill history, a Prinsenbouwen book. It was actually printed during the war, but the research was done before. So a lot of things that modern wind engineers could have known is when they were looking back to the Prinsenbouwen book. I do have an original copy of that one. I'm lucky about that. It's still very interesting to read about the research that those people did in those days. Modern wind energy research started actually in the middle of the 70s, because we had the oil crisis, or the petrol crisis in 1972. Some of you still may know that. So that initiated actually some research in the Netherlands on using local energy sources. And we do have a lot of wind in the Netherlands, on the coastline and certainly offshore. So one of the things that was happening there is there was external funding for research. And the supervisor of that research was Theo van Holten. He was a researcher in helicopters. And you can imagine that from helicopters to wind turbine rotors, as some step, but of course there's kind of some knowledge that you can use for that. And I, together with Gijs van Kuik, actually were the young researchers. So we started researching in January of 1977 into a kind of very innovative project, which is called the TIPFAME project. I'm afraid I cannot tell too much about it, but it was about improving the performances of wind turbines. And of course, if you can get more energy out of the same size, it should pay off in terms of the cost of energy. But he was in aerospace engineering, of course, because of his helicopter background. But there was not a lot of support. I mean, in those days, wind turbine researchers were considered as the alternative researchers, long-haired, geitenwolle sokken, as we say in Holland, etc. So it was not very much appreciated. That meant that we had to use facilities from outside the TU Delft. So we used a wind tunnel in Waddinxveen, which was near Gouda. We wanted to build a research turbine, that we were not allowed to build it on the premises of the TU Delft, on the campus. So it had to be built 30, 40 kilometers from Delft in Hoek of Holland. And in those days, young researchers didn't have the money to buy a car. So Gijs and I had a bike to go to work. But this was the car of Theo van Holten. And it's now a nice vintage car. And we drove that quite often, either to Hoek of Holland or to Waddinxveen to do our experimental research. Okay. What actually, I'm missing one. That's crazy. Should be a slide inside this, because actually in 1984 there was a big cross through this research. The reason was that there was so little support for continuation of the research that Theo van Holten went away, and he was the only person that was appointed to do research, and the rest had to be sourced out. That was in 1984. Actually, I was the only one official survivor, and we could start then again with something which was called the Institute for Wind Energy. There was something that didn't belong to any of the faculties of TU Delft, but we simply had to initiate this Institute for Wind Energy because there was still a grant from the ministry. So the ministry wanted the TU Delft to do research. TU Delft didn't want to do research, so we had to set up our own institute to do research. It was a kind of a mini faculty in between the other faculties. And there was also money in that funding for infrastructure, for a new test field and a new wind tunnel, because we needed a wind tunnel in Delft to do the research. In 1987, this test field was opened at the TU Delft campus. It was on a place which is now covered by one of the buildings of Yes Delft, so from the techno starters. On that spot, we had a test site, and it was a very nice one. You can see a model of the test rotor somewhere over there in the exhibition. It had a very advanced rotor, and it was done for doing rotor research. So we really want to understand the details of the flow around wind turbine rotors. This is me as a young researcher working on the nacelle, because the nice thing was that we could turn this thing down and up again to change anything on the rotor and put it up again and then start rotating. So now here it's down on the ground. And this is, if it works, doesn't. Yeah, sorry, animation don't work, it's a pity. But here you could see actually a view from the rotor down, where you can see all the differences in the flow caused by turbulence in the wind. And we also had our first vertical axis wind turbines. And this one is operating. Okay, fine. Make some noise. And we, in the end, started as well to look into offshore wind already, because we had a dedicated, what's called monopile foundation in Delft, in the ground, in the peat, with a real wind turbine on top to see what the dynamics are of these type of foundations for offshore structures. I was back in the 80s already. Then again, there was some issue. We were able to continue our research, but there was actually no vision on where to go to in terms of wind energy research in Delft. Quite some things were published in the Delta on, well, is there a center of wind energy? Is there no center of wind energy? Where can we find the center of wind energy? It took a long time. In the end, in 1990, civil engineering, they decided to take wind energy under their umbrella. And we got our first part-time professor, Jan Dracht. Why civil engineering? Because in 1986, civil engineering was asked to do the testing on the steel rotor blades that were designed specifically for a wind farm in Friesland, Shakespearean wind farm. I think that was the one and only larger wind turbine that was manufactured in steel blades. The reason why they took steel was because steel was the only material for which they had long-term fatigue characteristics. I mean, composite blades are in the end a lot better, but you know, in those days, we didn't really know what would happen if you would have fatigue loading for 20 years on a composite structure. So that's why they chose the steel. Well, fine. Then in 1996, we finally had this Center for Wind Energy, this Institute for Wind Energy. And Gijs van Kuyk, my colleague, became the first director of that. And in 1999, we established a larger group of different faculties collaborating together. So yes, that was very good, and it worked very smoothly, and we thought we could continue like that. But forget about it. We had a second reorganization. Civil engineering refocused. They said, we don't want wind energy, so okay, let's throw these guys out and just see what happens next. Luckily, then wind energy continued at Delft. In aerospace engineering, they finally picked it up in 2004. They were not too afraid anymore then of wind energy researchers. But we had a very nice testing facility at the campus. It was too expensive. So they didn't want to continue that. It had to be removed. This is, by the way, the group of people that worked in wind energy in those days, connected to the test field. The blade fatigue testing was also outsourced because it became, I don't know, too large, too commercial, to a different entity called WMC. 7 experienced researchers lost their jobs in wind energy. Some of them got other jobs within the university, but some also disappeared. And there still was this promise to realize the wind tunnel. We did have the test facility, but that was taken down, so that was a pity. But the wind tunnel still was a promise already from 1984. And we finally got it in 2009. So finally, in 2009, we had the right facility to do experimental work on wind turbine models, on kite models, etc., etc. And yes, we set it up a curriculum so that finally, in the end, students were able to choose for a study in wind energy. It was a master curriculum, there was a minor offshore wind, We had about 30, 40 PhD candidates, and we collaborated all together in a European wind master. In terms of results, I always show this picture, and you have to look very carefully, because here you can see the modern wind turbines of the 80s, and these are the modern wind turbines in 2015. So that's a development with a factor of 40 increase in power, the amount of power that's installed, a factor of 8 in production, so the amount of energy that they produce, and we did it in 30 years of R&D. And I've no time to do it now, but I sometimes compare that to what the aircraft industry has been doing, and we at least are twice as better as the people that work in the aircraft industry on aircraft research. So we really did a good job in terms of improving our knowledge. Well, what we got, or what we actually contributed, is many things. But I mean, to just mention a few, we did a lot on the aerodynamics, of course, so the airfoil design and the blade design, etc., etc. There was a lot done on the controller design. This was usually done within mechanical engineering. So optimizing the control of the wind turbine is also important for example, reducing fatigue loads and optimizing performance. And we also did, with electrical engineering, a lot of work on what we call direct drive generators. And direct drive wind turbines have the advantage that they don't have a gearbox. So it's a much simpler design, and less components means less maintenance. So that's one of the main advantages. As I said, I'm a certified miller, and I'm a modern wind turbine researcher. And I got a chance once to combine these things in a windmill, a windmolen, which is called the Nolet. And this is one of the windmolens of Schiedam, so it's not that far from Delft. And I always call this the world's first and only stealth wind turbine. Because it really looks, isn't it, like an old windmill? But it's a modern wind turbine. Why? Well, because it looks authentic, but the aerodynamics are modern. So all the knowledge that we got from designing modern wind turbines, we reapplied into the old windmills. And inside, as you can see maybe in the back, there's a modern gearbox and a generator installation in the nacelle, but you can't see it. It produces electricity, green electricity, and the company, it's a distillery, uses that green electricity for the bottling plant, so where they put the Geneva or whatever they have into the bottles. So it's really used locally on the premises. And one of the things we had to take care of, that it had to look like an old windmill. So these wooden fences that you can also see on the exhibition had to be added. I mean, it's not good for the aerodynamics, but we had to add that in order to have it looking like an old windmill. And of course, inside, this is a TU Delft modern wind turbine designed airfoil, which we applied for the windmill. So that was really fun doing this again as somebody that has the heart both in the old windmills and in the modern wind turbines. Okay, where are we now? What have we achieved? We have now integrated design models, so we can now integrate aerodynamics with control, etc., with the dynamics of the system to optimize. We now make the largest rotating machines on Earth. Sizes are now beyond 200 meters diameter. It's really not possible to imagine that. I mean, the towers of the churches in Delft are about 100 meters, twice as large, one rotor. The largest composite structures on Earth, maybe you can see that, but there are a few people working on one of the blades. It's really, I mean, the root has a diameter of 7 meters, something like that. There are also 2 people near the nacelle. These are 2 people. So this is one nacelle. And this is a monopile. And here you can see also a guy walking. So this is what will be driven into the soil in the North Sea. They do that in a few hours, and then they put a large wind turbine on top of that. I mean, these are sizes that you can only make offshore, because they're, as you can see, they're really too large to be transported on land. And We also learned, apart from optimizing the wind turbine itself, also how to optimize when wind turbines working together in a wind farm. Because you can also do a lot in controlling the individual wind turbines to optimize the performance of the total wind farm. Right, and then there's a next game changer, because these wind turbines are now so large that it becomes more and more economic to put them on a floating structure and sail them out to the sea, which means that you can not only explore shallow seas, but also the deeper seas and also further away from the coast. So this is still fairly new. There are a few prototypes and a few small wind farms that are already operating, but by the sheer increase of the size, it becomes more economic. And when you're far off, you should really think about how can I transport that energy to land? Should I still do that with electric cables, which makes sense if the industry is near, but also looking into molecules. Try to make, for example, hydrogen offshore and then transport the hydrogen, because hydrogen you can transport via pipes, but also via ships. And then, of course, the rest of the oceans also become feasible in terms of harvesting wind energy. And when you think about that, and when you see where we could use hydrogen for example, producing steel, getting airplanes flying, and converting the whole shipping, which are also big areas where carbon dioxide is produced, then you would need about 5 times the current production of wind and solar. Well, this might seem ridiculous, but if I look back, an increase of a factor of 5 has been achieved over a period of 15 to 20 years. So if we really want, we could even do this in 20 years from now. There are a lot of fairy tales about wind. It should be unreliable, it should be intermittent, you need backup, it pollutes the power grid, you have voltage overshoots, negative prices. That's not true. I mean, these machines, smart controlled, with high power voltage electronics, etc., are very smart. But we use them in a stupid way. If they produce too much power, we curtail them. But you could also use them to improve the grid. And you can also do that locally. So quite of the issues that we have nowadays, you could in principle solve by locally, on land, coupling solar and wind energy with some storage. And then you can get rid of the congestion. But of course, then also the public, the people, should be willing to accept that. In the end, I think the whole energy transition will make our landscape look different. Because I always say, if you don't want windmills, you get high voltage lines. So, okay, the choice is yours. The point is, we still, although we're not branding it anymore, as wind and solar as the alternatives. So it's the classical energy system, and then wind and solar are the alternatives. We should go into a situation where we think different. We really think different. Which means we need to integrate and take wind and solar as the basis. And then the end solution will be totally different. As I said, a paradigm shift is needed. And for example, in this shift of paradigms, the use of nuclear power doesn't fit anymore. Because wind is very flexible, solar is very flexible, and the money that some of the government parties and some of the political parties want to spend in nuclear power is much better used if they put it into storage facilities. Because that's what we need with fluctuating wind and solar. But okay, that's my personal opinion. So what do we need? Much more, of course, interconnection, because then you can also make use of wind and solar from the other countries to send it over the oceans or whatever. Implementation of local smart grids, I already talked about that. So local wind, local solar, local storage. And then use the flexibility that you have of wind power. Because a wind turbine is the fastest controllable machine. You can control it downwards in 5 seconds. And no conventional power station can do that. So you can also opt for providing only 80% for what you can produce on an actual stage, and then keep 20% as a reserve. to compensate for variations. It should, of course, be paid off in terms of the economic, but the technique is there. You could do that. And then, of course, I talked about that already, what they call power to X, so power to molecules. And, of course, we need to do something on recyclability. And there the industry is making steps. Now we are in a position that some commercial manufacturers already provide wind turbine rotor blades which are recyclable. And if we are able to solve this, then I think we learned a lot. This is me when I was a student in old windmills. And this is part of my career. They used me as an energy snack in 2022. That was the 180 celebration of TU Delft. Nowadays, I have my avatar, of course. I have to go. This is my AI avatar. And I think with wind and solar, the future can be bright, beautiful, and sustainable. This is a beautiful picture, isn't it? And it can be, if we really want, powered for full 100% by wind and solar. But you need to cooperate. We need to get our heads together, see that is a common challenge that we can tackle if you want to do it. Okay, thank you very much for your attention.
What's the right button?
Yeah.
This one, the big one?
Yeah, the big one when it comes up.
Whew. So, thank you. This should actually be a movie. Super, thanks. So my name is Roland Schmehl, and I will introduce you to airborne wind energy together with Jelle. And Gerard, I hope that we can contribute to the paradigm shift. I think that's a very good way to see it. Here you see a kite flying and producing energy on the island of Aruba next to the Father Pete wind farm that you see the turbines in the background. That was a very nice setting of Kite Power, our spin-off company, in 2021. This should also be animated. Okay. This is how the concept works. So we fly a kite connected to a tether to a ground station. The ground station has a drum with a connected generator. We reel off the cable, the tether from the, let me try this again. Oops, is there a way to back? Sorry, can you run this video again? Okay, so we fly these figure-of-8 maneuvers to pull very hard on the tether, and that's when we produce the energy in the generator. Think about a yo-yo. Once we reach the top, the maximum length of the tether, the kite is depowered and pulled back by the motor. That consumes a little bit of energy, but netto, we actually produce energy. So we do need storage, also very important for this type of concept. There are a few, let's say, opportunities or advantages why we go towards kites, and of course we also have our challenges. As for the opportunities, a kite needs a lot, or an airborne wind energy system needs a lot less material than a wind turbine. If we go offshore, we calculate something like 90% mass reduction for the same amount of energy. Then the kite can be adjusted to the altitude. So if the wind blows stronger at higher altitudes, we can fly higher. If it blows harder at lower altitudes, we can fly lower. So this adjustability increases the so-called capacity factor of our system. And of course, you can imagine we can transport the system much quicker to a location, deploy it there, then move it somewhere else. So we have increased mobility. On the other hand, a flying kite and operated from a ground station is more complex. There are an infinite amount of degrees of freedom by flying the kite. That all needs to be controlled. Also, the ground station needs to be controlled. We require reliable and robust control, and we depend on high performance materials. You see here, the tether is made of Dyneema. That's a plastic material that is stronger than steel, and also the kite itself is made of plastic. And of course, the regulatory framework needs to be adjusted. Okay, 2 slides with a bit of technical content I have to introduce. The material use, that's one of the advantages that I discussed. You see here, this unit is the mass percentage of a 100 kilowatt system that is currently been manufactured. You see all this is the ground station. In relation to this, the kite control unit, the little robot that controls the kite during the flight. We will see this in later slides. The tether and the kite are small contributions compared to the ground station. In a wind turbine, this is actually a reasonably small part. The nacelle and the generator makes up for 20% together with the rotor in terms of mass. You see here that all the mass is now in the generator, and for the rest, very little material. We also need to think about the replacement of the materials here. Kite tether, mainly because they degrade over lifetime, so they have to be replaced. That's something we need to take into account, and we did that here in a study. Global warming potential is another metric, so the CO2 equivalent per megawatt hour energy produced is here distributed over the components, and you see again the ground station is the main factor. So what's clear from these pictures here is, from these diagrams, is we can dramatically reduce mass, a bit less dramatically reduce the environmental impact, but still significantly. That's one of the key drivers for our motivation to go into airborne wind. And then a second important driver is, you see here, power curves for a classical turbine and a kite power system, which can fly higher, as you see here. We can harvest at lower ground wind speeds than the turbine, meaning this region here of wind speeds we can actually exploit. And that has to do with this adjustability of the operational altitude. So, and from now on, I think I have mostly graphics. In Delft, we had a pioneering team, I think, one of the earliest, but by now, airborne wind energy is researched and developed all over the world. You see here maybe a few highlights. In the US, we have Windlift, and then in Europe, Kite Power here in Delft. We have Kite Mill in Norway, Sky Sails in Hamburg, and Enerkite in Berlin. But there are many more institutions involved. These are the current sites where airborne wind energy is tested, partially already commercially. You see most of the sites, the green ones are the active ones. They are in Europe. Here in Ireland is the test center of kite power, and also in the Netherlands we have some operational sites. But since 1 or 2 years, China is actually ramping up. And you see that they have some sites now with quite large facilities installed recently. It all started here in Delft with Wubbe Ockels. This is a photo from 2013. He was the pioneer of airborne wind, patented the Laddermolen in 1999. And from this moment on, basically, we have a continuous, let's say, build-up of knowledge, and publications also spun out 2 companies, Ampex Power and Kite Power, I think 2 important players. A few images of how this early research looked in Delft. You see here snow on the airfield at Falkenberg. This was our ground station, tether going up into the air and flying. Here the crew on the control center, over here in the background, one of the members trying to hotfix some bugs in the flight software. And then this is how we launched the kite in these days. This is a 25 square meter kite, our so-called V3, with 3 students here holding the kite so that it doesn't fly off. Another one holding the tether with the kite control unit here. In the foreground, you see this kite control unit uses 2 micro winches on tapes to actually control the kite like a kite boarder does. And it's wirelessly connected to the ground station where the control center is. And then countdown, then we lift off, and then we are flying solo. You see here the kite, the ground station at Falkenberg. Controls needed to be in check at the time. We already had automatic control. So once the kite was launched, we could press a button and it would gently fly, figure of 8 maneuvers, harvesting energy. And in the evening, you have to land. All was done manually, and you see this is maybe not the most safest thing to do, but nothing happened, luckily. And then we wrap up and go home. Winter conditions demonstrates, kite flies in snow, absolutely no problem. We then were lucky to get a larger EU grant. Actually, that was, I think, Hester Beil, our dean then. She was the one who signed the grant agreement, which is something really nice. And with this grant, we were able to develop a large ground station, a 100 kilowatt ground station, hire a team, and then collaborate with 3 European partner companies to commercialize the technology. And this is a picture from a few years ago. Also here on an island near to Zeeland, where we used the kite to charge an electric car completely off-grid. I think this is one of the application scenarios you can think of. Our research group a year ago, and Kite Power here in Delft in the Kabel district. They have a large facility there. And I think this is the 60 square meter or the 100 square meter kite. Would you know? I think it's the 100 square meter. Yeah, it's pretty large. So this wing gets larger and larger to pull more power from the sky. And that's a very nice feature of kites. They are easily scalable without too much costs. And the bigger the surface area, the more power you can get out of the wind. Then we were also lucky to be able to establish a test center in Ireland with the help of RWE. You see here the ground station with battery, then the hangar of the test center. And I think since about 2.5 to 3 years, the Irish crew is continuously testing new kites on a weekly basis, I think 2 or 3 flights per week. Also using operators from Ireland who were trained and certified kite pilots, which is a new profession in our field now. That's the Delft team visiting Ireland. The operations in Ireland, you see, it's peat. You cannot go there by car, so the kite needs to be transported to the launch site with this vehicle and then put on a launch trailer and unreefed. So all these operations are not manual anymore, but automated with mechanical infrastructure. That's the onboard wind turbine suspended below the kite for the avionics of the system. And maybe just before I finish with the video, a few key numbers. So we are now looking at 24-hour continuous operation of the system before we land, typically. That's the 3.1 million of deployed projects that we have executed since the foundation of the company, flown more than 400 times, 24 employees. And we have these 2 locations, one in Delft and one in Ireland. And if you could get this video to run with audio, please.
At Dura Vermeer's modern construction sites, electric machinery is already in use. Working without emissions is becoming essential. But can we do even better? As the wind rushes past us, we ask ourselves, can we harness its power? And what if we could turn that wind into energy? 200 meters up, where the wind is strongest, we're putting it to the test. As the first construction company in the Netherlands, we're exploring whether airborne wind energy, generated by Kite Power's kites, can provide reliable power for our work sites. A mobile system instantly ready to deliver. The kite loops in figure eights, pulling hard on a cable. The cable unspools from a drum, driving a generator that transforms motion into electricity. That power is stored and managed on site, silent, flexible, and independent of the grid. It opens up new possibilities, especially where traditional infrastructure can't reach. Power for tools, power for machines, like this Volvo truck, already electric, now driven purely by wind. Dura Vermeer aims to lead. That's why we innovate, with pioneers like Kite Power and Greener Power Solutions, who enabled seamless integration between kite and battery, turning wind, flight, and smart storage into zero-emission energy on site. We're searching for answers. Can airborne wind power become a stable part of our sustainable future? Can we reduce our dependence on fossil fuels and build in quieter, cleaner ways? Every test, every data point, every breakthrough brings us one step closer to the energy-neutral construction site of tomorrow. We're not doing this because it's easy. We're doing it because it's worth exploring. Dura Vermeer, realizing ambitions.
Thank you. I think with this, I would like to hand over to Jelle. So Dura Vermeer was our first commercial customer, and I think they were quite happy about what we did for them, and that's why I wanted to show this. Please.
Thank you.
Oh, nice. Yeah, then we get to my topic. So for me, it also started similar to how it started for Wubo, the first Dutch astronaut who loved kites since he was a little kid. It's a bit similar for me, but I like to go on the water with them. And these days, the kites are not only used to produce energy and not only used to pull people across the water, but also boats. And the kites are getting bigger and bigger and bigger, similar to the wind turbines, which were also getting bigger and bigger and bigger, right? Slowly starting to produce more power. And it's interesting to look a bit into how these kites actually work. And for that, I have a nice video here. And it's a bit similar to, there we go. A bit similar to how a kitesurf kite works. One pulls on the lines, and this creates a deformation in the wing. So the wing initially is nice and straight. I pull on one side, the wing rotates, and as a consequence, the aerodynamic force factor also rotates and the whole kite starts to roll. And in that way, we can steer the kite left, right, everywhere we want it to go. And if you want to simulate this, you need something called fluid structure interaction simulations. And that's quite a mouthful, but I will talk you through it. So first, we take a shape here on the right, and we use an aerodynamic model to get an amount of force, an aerodynamic force. Then we give those forces to our structural model, which now computes the new shape based on the forces. But then we have a new shape, and we need to give this shape again to the aerodynamic model, which based on this new shape gets a new force, and so forth, and so forth. And these iterations we solve using computers, of course, and the computer is getting faster and faster and faster, and it allows us to include more and more details. And as I said, to do so, we need an aerodynamic model, and we need a structural model. We use all sorts of modeling techniques for this, but I will not bother you with that today. I think what's interesting to highlight is why actually are these simulations so relevant? Well, with the kites becoming bigger and bigger and bigger, we can no longer use traditional methods. that we stole from the kite design, the kite surf industry, where we take the kite to the beach, we fly it, and we feel a little bit how it works, and then we're like, no, it's not right. This doesn't work anymore at 200 square meter. This is too big. We need to predict it upfront to optimize our controllers, to optimize our flight path, to optimize our design. Because what we do not want is that the kite, because of misprediction, falls out of the sky. Oh, video not working. Anyways, so the question arises then with these simulations, are we making the right predictions? Because if we're not, then yeah, what are we basing our optimizations on? And to answer this question, we need to go to the wind tunnel. And in the wind tunnel, we can start simple. We can take the kite, slice it in half, take the airfoil, so as it's called, and we place it inside the wind tunnel. Then inside there, we can rotate it around, put some flow to it, measure the forces, and we can see if we make the right simulations. We can also go one step further and look not only at the external loads, but look at how the flow behaves itself. And one way to do that is using oil. And then you get beautiful images. To me, this is supposed to be science, but it's more art, right? Here in the front, the illuminated part is the so-called laminar separation bubble. And then slowly towards the back, we see it fading and gravity taking over and dripping the oil flow down. Besides oil flow, we can also use other techniques, stethoscopes, infrared cameras, and then we can study things like the transition from laminar to turbulent, where first the flow is laminar and then it goes to turbulent. And the stethoscope shows the same story, because when the flow transitions from a laminar to a turbulent state, it becomes a lot more noisy. And the stethoscope essentially is a microphone, and this allows us to hear this increase in noise. So then, once we're done with the airfoil level, right, the mid-span slice, we go to the kite level. And we take the kite and we put it to the wind tunnel, which exists thanks to legends like Gerard, thank you. And then we can do some really cool measurements using carbon fiber kites to check out again, what are the loads, how is it doing, how do the smoke trails go over the wing, is it as we expect that it would be? And then once we're done with the loads, we can go back and go one level deeper again. How is the flow actually behaving? What is the flow topology? How are the structures looking like? And for that, we need lasers. And I hope this video works. Nice. Yeah, so this is how it looks like when you're testing with lasers inside the wind tunnel. It's very chaotic. But if you look well, on the left, you can actually see the kite standing in the flow field. And I'll explain briefly how this actually works. So we use a camera, we use a laser, we use a smoke machine, and then the smoke particles, they're accelerated by the wind turbine that powers the wind tunnel. And these smoke particles we illuminate with the laser, and then we take pictures of those particles, and then we do a lot of algorithms and coding and processing and whatnot, and then we find something about how the flow actually looks like. And we find something about the flow structures, the magnitude of the flow around the airfoil. And then, of course, the question is, do these measurements relate to the simulations? And yes, we see the same flow structures back. We see the same areas of high velocity and low velocity, and curvature and wake and vorticity and whatnot. So this is all aerodynamics. But as I said, the deformations are critical. So we need to also look at how the kite shape moves. And for that, we can do in-flight measurements. This is a very recent picture, and I think that's also the reason why I am here today to talk about what is happening right now in wind energy. What is the state of the art? This was made last week in Ireland. The people are all in the crowd. Thanks for coming. And what was used here were cameras to track markers around the kite. And by tracking the markers, a bit the same as with our eyes, using 2 cameras to track the markers, you can track their relative position and you can check what the shape changes are over time and overlay that next to the simulations. And by doing these kinds of efforts, we hope to build better and better models, and these models can then be used to build better and better kites to produce more and more electricity. Thank you.
Can I invite Theo and Gerard up to the front for a moment? Lot of content, no shortage of content. But I wanted to give the audience a little bit of a moment to throw a few questions at our speakers. So we're running a little short on time, but let's just get into a few questions.
I was really inspired by all the speeches. Thank you for that. And first of all, I want to thank Gerard as well for building that nice building in Delft, where I also started my company before the building got demolished. So that was back in 2005. After that company, I joined Kite Power. And looking at the strandbeest, I'm wondering, could we build a kite-powered strandbeest? Or even use a strandbeest that is flying with the kite and then controlling the kite surfaces? That would be very cool in my mind. What do you think, Theo?
Well, in fact, the most recent animal, which you may have seen in the video, a very high animal. In fact, those are kites up there, and so, in fact, I'm just copying their work. And, sorry about that. And without any credits, I just do it on my own.
Anybody else? At the front? Did you have something?
Thank you. It's a question that might be related to all speakers, so all use of wind energy, but maybe a little bit more directly applicable to the last part on kite energy. I was wondering, how do you deal with the change of environment, which seems to be constant in comparison to all types of different energy resources?
What kind of change?
So I really mean like the fact that the wind would change direction, magnitude.
I think that's where wind turbines and kites are pretty similar. You need to take it into account. The wind turbine can yaw to adjust to the direction. The kite ground station also yaws to adjust to the wind direction. And of course, you can also control the flight pattern of the kite, and in this way adjust. The kite system is just very similar to the wind turbine, but has more degrees of freedom because it has a free-flying rotor blade, so to say. But I think that's more or less.
Yeah, what I could add upon that is that when I gave my inaugural speech as a professor in aerospace engineering, I did forecast what the size would be of a offshore wind turbine in 2020. I was completely off. There was a factor of 2 in between my forecast and what happened in reality. And one of the reasons why the industry, together with the researchers, was able to get into those big sizes is actually that these modern rotors or these modern blades are very smart. So you can imagine that they are of such a size that they will deform during their rotation. That is something that is designed into the rotor to alleviate load fluctuation, so your fatigue load is reduced. Also, the blades themselves, they change position during one revolution in order to take into account the difference between 50 meters height and 300 meters height. As you can imagine, the higher you get, the more wind energy you get, but you have to adapt the wind turbine there. So by having integrated design models which are validated through experiments, we were able to go to beyond sizes I never could anticipate when I started, and certainly not also 20 years ago. And we don't know where the limit is because we still keep on learning that. So the combination of theory, experiments, and tools make this possible. And similar things hold for kite. So I don't know where the maximum is in terms of the size of a kite bar, but it might also be very large because you learn by doing these things, by doing these experiments.
I think I should make a prediction on the size, but I will hopefully be wrong.
Don't do that, no.
And Theo, would you mind also telling us about the intelligence status of the strandbeest?
I'm a bit afraid to answer this question because it's so primitive comparing to my neighbors. It just do it by hand, so I adjust it to the wind by rolling up the sail a little bit. And there are two kinds of strandbeest. There are the ones who just follow the wind and the ones who walk sideways on the wind. And of course, aerodynamics on the sideways walking animals is a lot more complicated than the ones which walk with the wind. And last summer I had a crosswalker, that's what I call it, on the beach, and I noticed that aerodynamics of the sails was improved so well, and it was, I think, at least 3 times more force by just using the laminar stream, the flow along the. I don't have a wind tunnel. That's a problem. Maybe my neighbors can help me with that.
Hello, thank you for the speeches. This one goes to Theo Jansen. I was just wondering, it really stuck to me how you said that you saw your work the miracle of creation, and how the strandbeest evolves through the reproduction of students, through the mentality, through their curious minds, which eventually sparked the creativity within us. I wanted to ask more about your creative process. So what is your relationship with this creative nature, and how do you funnel down from an idea or some inspiration into the wonderful beasts that we do see in the beaches?
Well, in the beginning, in 1990, I thought I was a sort of a god, I only had to materialize my ingenious ideas. And then during the years, it turned out that my ingenious ideas didn't work. Scarcely. In fact, it came to a sort of evolutionary process. You could see my ideas as a sort of mutations, and most mutations don't work, but sometimes something coincidentally happens under my hands by just playing with the tubes. And then a new door opens to the future, and so I came to the conclusion it's an evolutionary process. By just playing with the tubes, every day something changes. So the path is very capricious and very unpredictable. And in the end, when the beast is finished, I'm surprised myself how beautiful they became. Not that I tried to make them beautiful, because I think the beauty became out of just by following the advices of the tubes, you could say. And by using just one material, you're forced not to follow your brain too much. You have to follow the tubes, the material. So the material dictates me, in fact. So it's not very creative, in fact. I just have to listen to the tubes, because after a while, the tubes start talking to you if you play enough with them. And I think the same process is happening with you, because it's an evolutionary process. Only the steps which you have to take are a lot larger than I have to take, because I can change everything in one day or a few hours. And if you have to plan something, then of course at least a few months, and then you wait for results. And I really pity you, because you are you have to do this kind of predictions. And I, as an artist, I can afford myself some failure. Nobody would start crying if I fail on the beach, and even not myself. And for me, it's easier because I can just afford to play a little bit more. And you have to be very serious.
Yeah, but still play. I mean, what I do see is a really big similarity between the three of us is something you could call experimental or empirical smartness. Mm-hmm. We all try to make our machines more and more smart. Also, your strand-based, they become smarter and smarter and more independent. And that's a kind of line that I can see through the three presentations. So that's what we all need. I mean, we could try to do a lot of calculations, but in the end, the experiments that we do are key. So we learn very much from doing things. And yes, the cycle is a little bit longer, but the principle is the same, I would say.
Well, maybe one exception is as well is Jelle, because he uses his computer models, and you're able just to change a few things in a few minutes, and then you can just collapse a kite and let it fall down, whatever. And so that's the nice thing about this time we are living in, that engineers can become artists again by just playing because of these simulations. So with my fellow artists here, I hope we can provide you for a new future.
Well, thank you. I think that's a great place to conclude the program. So please, a round of applause for our speakers again. And thank you all. And for the speakers, for each of you, I have a model tram for the tram exhibition, as well as a little snoopia from the library. So see me after the talk. But once again, thanks to the speakers and also the content of the exhibition. So let's not forget we're here to open the exhibition. So I hope that we still have a little bit of time to celebrate. We have a small Samboro action over to the corner, and as well as two large exhibition stations. One is representing Theo Jansen's work, and the other one gets into the kites, the turbines, and the historic molen. And I also wanted to just acknowledge that there is a very large turbine blade outside. So on your way out, leaving today, please check out the scale of that. So that's just a 20 meter long blade. So this is actually quite small than some of the blades that we've been discussing earlier today. With that, I think we're just going to get to the celebration. So thank you very much for coming, and please mingle with the artists and speakers afterwards. And please check the online program for future events, because we want to end with the 15th of December. There's a large discussion panel in the aula, and we hope to see you all there, if not before.